Welcome to the lecture. In today's lecture, we'll be discussing how we can convert the original system, which is maybe in the coupled form, to a decoupled form, so that we can easily check whether the system is stable or not by looking at the diagonal elements of the matrix. So this concept we call linear transformation. We'll map the system from one domain to another domain using some transformation matrix, and that transform system we call sometimes canonical form. So let's start the lecture, and I hope you'll understand some important part into the lecture. And so we are going to cover the contents. First is state transformation. This is also called diagonalization approach. And also we'll discuss the eigenvalues and eigenvectors, and how they will, these are the important parameters to come up the transformation matrix. So if you have a system, for example, if you have a system extract some scalar system x equal to ax, and this is, let's say, this scalar system, and for example, the initial condition is given to us maybe 4. So if you solve this equation, we can write x of t equal to the power at x over, or we can say 4 to the power 18. So it means if you have a system in this structure, it is easy for us to determine or comment whether the system is stable or not, because the here x equal to x, there is no other parameters involved in the system, other states. The system which is the derivative of the state, the same state available at the right hand side. So here it is easy to solve and easy to comment how the system is going to behave based on the polarity of the A matrix. Sorry, A, this is the scalar elements. So if A is, for example, if A is negative, we can comment that. So we can say x of t equal to the minus A of t. You can say. So in that case, it is 4 anyways. So the system will be something like this. It will start from 4 and it will exponentially decay to 0. And so based on the polarity of A, we can comment whether the system is stable or not. The same approach will follow in today's lecture. So how we can come up the some diagonalized form of the original system, and it will be easy for us to comment whether the system is how the system is going to behave or stable or not. So so our main motivation is, suppose we have system x1 of t equal to x1 not an x2 dot. For example, the system matrix A1, A2, A3, and A4, and we have the vector of t, x2 of t. Now, if you find some way which can help us to convert the system some other domain, maybe Z1 domain, Z domain, Z2 T, and where we can write the system matrix in this form, C1, for example, 0, and C2, the diagonal elements, and G1 of T, G2 of T. So by the polarity of values of C1 and C2, we can comment the system is stable or not. So here, this process is called linear transformation. So here we'll be using some matrix T, which is actually linear transformation matrix, which will help us to get this form. And this is also sometimes we call canonical form. So let's start. So here we have the original system. For example, we have the system which may be in the coupled form, x dot equal to ax plus bu. So here we are assuming A is not diagonal matrix. Okay. So here we are introducing a new variable z. Here, z is a new variable. We are defining new variable, and this new variable is related by the following equality. So we are writing x of t equal to, we are writing t z of capital Z, so vector. So here, using this transformation matrix, which help us to transform x domain to z domain. And now, so this is basically we call this matrix actually transformation matrix. Yeah. Okay. Now, if you substitute this expression or this equation, the original state equation, we can write, we can get x dot of t equal to t3 dot t equal to, we can write at gt plus b ut, or we can write g dot t equal to t inverse at gt plus t inverse b ut. So this is the new state equation. In Z domain. Okay. So let us define A dash equal to T inverse AT and B dash equal to T inverse B. This is, and using these terms, let me define this equation number 1. Let's assume this is the equation number 1. So if you substitute this parameter in equation 1, we can write z dot t, we can write a dash zt plus b dash u. Okay, and similarly, so this is the state equation, and let me define, this is equation number 2, and the output equation we can write y of t equal to cxt, or we can write ct zt, and also we can write c dash zt, where c dash equal to c2. So we are having two equations. One is the state equation, and is the output equation. and this is the state equation, right? And now the question is, how to find this T matrix. But before that, here I should comment that the system which you have found here actually this A dash actually diagonalized. Now how it is coming, we'll explain. So this is the diagonal system. So by the looking of the diagonal elements of A dash, we can comment how this Z parameter or state going to behave over time. This is, we can easily comment. You see, this is the Z1, Z2, Z3, this Z vector, and this is the dot, and we have the diagonal element. So the system is completely decoupled. So if the states are decoupled from each other, we can easily find the solution. So that is why it is very, very powerful technique. If you can convert the original system, which is in the coupled form, into decoupled form. So now the question is how to find T matrix. So now we'll go through some linear algebra concept to find this T matrix. So here, the T matrix, first we have to find the eigenvector. Okay, before that I should write something. The T matrix actually, T matrix can be formed by the eigenvectors. So we can say T is nothing but if there is 2 cross, suppose for example we are using a matrix 2 cross 2. So we'll have 2 eigenvalues. For the corresponding eigenvalues, we'll have eigenvector, right? So for this 2 cross 2 matrix, we'll have 2 eigenvectors, which will be V1 and V2 can write like this. So this is nothing but the transformation matrix. Okay. Now the question is how to find eigenvalues, because eigenvalues will help us to find the eigenvector. So eigenvalues, if you remember in our earlier lecture, we have used lambda I minus A equal to 0. So if you these are the eigenvalues, this lambda actually eigenvalues. So if you solve this equation, we'll get eigenvalues of A. So this is also we call sometime characteristic equation. For a particular system, remember the characteristic equation always fixed for a particular system because we are getting the A system matrix here. So always characteristic equation fixed for a particular specific system. Now, this characteristic equation of the expand will have in this form. We can, if you are using is n cross n matrix, the order of the characteristic equation will be also n. Lambda n plus an lambda n minus 1, an minus 1, lambda n minus 2. So it will move like this, equal to 0. So if you solve this equation, it will give the list of eigenvalues, or we can say the roots. Basically, if we solve, we'll get the roots. These are nothing but eigenvalues. Okay. Now, if you know the eigenvalues, if you have the eigenvalues, and if you have the A matrix, which is here, then easily we can find the corresponding eigenvector. So as you know, the eigenvector and eigenvalues satisfy the following equation. So eigenvector eigenvalues and system matrix satisfy the following equation. A vi equal to lambda I vi. So for the particular specific eigenvalues, we'll have eigenvector. And this is also you can solve like this. Lambda I minus A and vi equal to 0. So from this equation we can find, because here the only unknown, because from this equation we'll find the eigenvalues. And so in this equation, the only unknown is the eigenvector, because A is already given to us. So now, if once you have, this is a very important note, if when the, let me write it this way, when the system has distinct eigenvalues, we can find the system into a canonical form where the state equation will be in decoupled form. We'll take an example later in this lecture, then it will come to know. So finally, our T, the transformation matrix, which is nothing but T, can be formed if there are n eigenvalues. So those if there are n eigenvectors, these will come into the as a column in the T matrix. Yeah, this is how we can form the this is how we can form the transformation matrix. Now, we'll go back to our system matrix in the transform domain. So this is what we have found in our lecture. A dash equal to T inverse AT. So we can write A dash in the transform domain. We will have the system matrix. This is AT. System matrix will be in this domain. Lambda 1, 0, 0, dot, dot, 0, and this will be 0, lambda 2, 0, 0, and it will go like 0, 0, 0, the n. So in the diagonal, we'll have the eigenvalues. So this is how we can find in the decoupled form of the system. So only if you notice that in the A-dash matrix, we are having only the diagonal elements which contains the eigenvalues of the system. Now, in this case, if you want to write the state transition matrix, if you would like to write the state transition matrix, for the transformed system, we can write e to the power A dash T, because A dash T is the matrix in the transform system. So we can easily write e to the power lambda 1T, 0, 0, 0, 0 e to the power lambda 2T, 0, 0, 0, will go like this. Lambda, e to the power lambda NT, This is how we form. So we'll get the system standard state transition matrix in structure. Now we'll find the relation between how can we find the relation transform system matrix using the state transition matrix and linear transformation matrix. So let's look. So if you extend our transform matrix A dash using the power series form, in power series, we can write e to the power A dash t, we can write similar to our original system matrix, the way we wrote for the original system matrix in power series. Original state transition matrix for the original system, we had I plus A dash, the same structure we had, but here the matrix, system matrix will be different for the transform system. A dash square, t square divided by 2 factorial plus A dash cube, t cube divided by 3 factorial, and we'll move on. So now here what we'll do is, in place of I, we can write T inverse T, this will be identity matrix, plus T inverse is exist because all the eigenvectors of the T matrix will be linearly independent to each other. So T inverse exists because here we are considering the eigenvalues of the system distinct. If the eigenvalues are distinct, different from each other, automatically the eigenvectors should be different for the system. So that's why T inverse exists. Problem. So now, in place of A dash, we can also write, T inverse AT. This is what we defined before. The expression of the this A dash also we had. So we just put it here, and it is T. Sorry, this is T plus. We can write A dash. We can write A dash square. So we can write T inverse AT. I can write 2 times T inverse AT T square divided by 2 factorial. Similarly, we can write for the third term T inverse AT, sorry, for fourth term T inverse AT T, we can write T cube 3 factorial dot. So from this we can finally get the form T inverse T. We can write for this, that's the next term, we can write T inverse AT T. So in this case, these two will give the identity matrix, right? And this will be identity matrix. So from this term we can write T inverse A square T square divided by 2 factorial. Similarly here, this is identity matrix, this is identity matrix. So we can write from this expression, this term, we can write T inverse A cube T cube 3 factorial. Now if you take T inverse common from all the terms, we can write T inverse. We can take common from here. So we can write I, quite as I will explain, and it will be AT plus A square T square 2 factorial plus A cube T cube 3 factorial plus. So this is how we can write. So now from this we can write easily write e to the power a dash t equal to t inverse. So this is actually already we have this term already we had. So here it is nothing but e to the at. So now we can write so this e to the at. We can write e to the power at t, or we can write e to the power at equal to t e to the a dash t small t inverse. This is very, very powerful relation how the original system and transform system state transition matrix are related to each other. So now we'll find the solution of the state equation if they are written in the transform form, because we found the solution of the system which are written in the original state space form. But also in this case, also you can find the solution of the transform system, right? So now, in this original system we had before solution of x of t, we had x of t equal to e to the power at x naught plus 0 to t e to the power a t minus tau b u tau and d tau, right? Now what we'll do is here we'll substitute in place of this, we'll substitute in place of this, this matrix, so this term. So we can write in place of x t, we can write this is already the transform variable zt equal to, we can write e to the power at x naught, we can write t z naught plus 0 to t and if you multiply both sides, t inverse, so we can write multiply or simply t inverse, we can write zt equal to t inverse e to the at t g naught plus t inverse 0 to t e to the power a t minus lambda t tau to b u tau d tau, right? And from this we can write, so this, I'm missing one t here. Okay, so here instead of e to the power a t minus tau, we can write also in terms of the transform variable what we have found. So here we can write t inverse, we can write or we can write t inverse t e to the power a dash t minus tau t inverse we can write. So now here this t inverse and this will cancel out, and we can write z t e to the power a dash t z naught plus 0 to t e to the power a dash t minus tau t inverse b u tau and d tau. So this is the solution of the transform system. So this is the solution of the transform system. And if the anyways here if you consider unforced system or uncontrolled system, if you consider uncontrolled system, so this part is going to be 0. So we'll have this equation. So if you write with the system, it's not controlled or does not affected by external inputs. So we'll have the solution z of t equal to e to the power a dash t z naught. And now, if you would like to solve the original system solution, so it is quite interesting. So here we have found the expression of the z of t in transform domain. Now, if you want to get back to the original system solution, then how can you find? It is quite easy. So what do you know? We know x of t equal to x of t equal to x of t equal to t zt. So just simply will substitute this expression here. So we'll have t e to the power a dash t. So this is the solution. Also, we find the original system solution. So this is very important. How we can find the diagonalized system, and also how we can find the solution of the diagonalized system, and how eigenvector and eigenvalues are very important parameters for finding the linear transformation matrix. So let's stop it here. We'll continue from the next lecture, where we'll have example on this particular topic. Thank you.